Welcome to the discussion on ultrasound physics and fundamentals. My name is Rich Gordon. I have no financial disclosures to report. Now, in this presentation, I'm going to provide a basic overview to the physics of sound. Now, I am not a physicist. If you are a physicist, I apologize in advance for my very simple-minded approach to the physics of sound. I'll also discuss how ultrasound images are made and discuss some of the main differences between the ultrasound probes. I'll also warn you, I'm not a biomedical engineer, and I have a very simple-minded approach to that. So if you are a biomedical engineer, I apologize in advance. I'd also like to discuss the basic probe orientation and movements, discuss Doppler ultrasound, and review the common ultrasound artifacts. Now, all jokes aside, my goals for this presentation are to provide you the very basic knowledge necessary to navigate the common image acquisition and interpretation pitfalls that come with ultrasound physics. And the good news is you don't have to have a really deep, in-depth knowledge of physics to be a good sonologist. So let's start at the most basic tenet. What is a sound wave? Well, a sound wave is not going to be generated without a sound source. And that could be anything. That could be a person talking, it could be a dog barking, it could be a duck quacking. In our case, we're talking about an ultrasound probe, which is going to be the sound source. Well, how is the sound generated? Well, that source creates a compression of the medium that's surrounding it. In our case, the ultrasound gel that is applied to the skin, and then the skin and soft tissues there underneath. It creates that compression of that medium, and then that wave propagates through that medium around you, kind of like a slinky, where it's compressing and relaxing. And it takes on an organization similar to a droplet of water landing in a pool, radiating out equally from that source. And you can see as that sound gets further and further away from the source, it dissipates, also called attenuation. Now imagine for a second we could see the molecules in that medium compressing together and then spreading apart. This is what it would look like. We can see that medium compressing together and then that medium spreading apart, called rarefaction. It's similar to waves rolling in on the beach. These black parts of the diagram indicate the crest of the wave, the part of the wave that you would want to surf on, whereas the lighter portions represent the troughs in between the waves. And that continues along as that sound propagates through whatever medium is surrounding it. Now, if you're anything like me, you may have thought that the sound propagates through a medium kind of like a sine wave. Well, it turns out that's not true. If you were to actually plot your sound wave on a graph like this, where the pressure exerted on the medium is on the y-axis and time is on the x-axis, you would see a diagram that looks like this. Where as there is compression, the pressure is going higher in your medium, and then it relaxes, and then increase in the pressure again. And that's where that mental image of a sinusoidal sound wave comes from. And here's a plot of our various sound waves, all of different frequencies. Speaking of frequencies, what is frequency? Well, frequency is cycles per second. Well, what is a cycle? Well, if you look at the apex of this wave to the apex of this wave, that would be one cycle. It is the point on one wave that correlates to the same point on the next wave. If we assume that the time interval between our two dotted lines here is 60 seconds, this blue wave right here would be one cycle per second, or 1 hertz. Compare that to this brown wave down below, there would be 1, 2, 3, 4 cycles per second. So the frequency would be 4 hertz. Now, obviously, there is a broad range of frequencies associated with sound. For human hearing, it's 16 to 20,000 hertz. Diagnostic ultrasound is 2 to 15 megahertz. Now, there is ultrasound that is used at lower frequencies than this range. That is therapeutic ultrasound. So it's not used to create an image. It's just used to heat the tissues and provide a therapy. And we're not really going to be talking about therapeutic ultrasound in this course. How is the image generated? The ultrasound machine is able to generate an image based off of the pulsed echo principle. And it's similar to a submarine lurking through ocean water, sending out sound and listening for the return of the echoes. It's able to get an idea of the structures that are surrounding it. Well, we have our sound source here, which is the ultrasound probe. In the head of the ultrasound are crystals. They're arranged into piezoelectric channels. When an electrical impulse comes along and causes those crystals to vibrate, this is called a piezoelectric effect. And the reason that the crystals that are arranged in the face of the probe are called piezoelectric channels. And the piezoelectric effect is the conversion of electrical energy into a mechanical force. Mechanical force being something that causes compression or bending on a structure. In this case, it's the medium that surrounds the probe. So then you have your sound wave that is generated, and it goes out and bounces off of all of the surrounding structures. And you get a return signal in the form of the echo. Well, that echo represents a mechanical force that then again strikes the piezoelectric channels on the face of the ultrasound probe. That mechanical force is converted into electrical energy, and that electrical energy is transmitted back to the computer and processor of the ultrasound machine, and from there you get an ultrasound image. Well, you may be wondering, how does the software interpret that returning signal? Well, it comes down to the strength of the reflector, or how much of the sound that was generated by the ultrasound probe is reflected back to the ultrasound probe. You have your weak reflectors that are going to only reflect a small portion of that sound. Then you have strong reflectors, which are going to return a large portion of that sound. And this would be an example of a weak reflector. You can see our signal that returns is tiny. Well, the machine does register this, and the pixel that has been assigned to weak signals is a darker color, a dark gray. Now let's compare this to a strong reflector. You can see here we have a much stronger signal that returns to the ultrasound probe, and the color pixel that has been assigned to that strong signal is a bright white pixel. Now, obviously, there's going to be some reflectors that aren't really reflectors at all and don't return any signal. You can see there that our sound passes right through our target. Because there is no return of signal, it applies a black pixel. We describe this as anechoic. Now, I'm misleading you a little bit. Generally, when you use the terminology hyperechoic or hypoechoic, you are comparing two different pixel shades. It's not really to describe one pixel, except for in the case of anechoic. I mean, a black pixel is a black pixel that tells you that your target is anechoic. However, when comparing the white and the gray pixel here, you would say that this pixel is hyperechoic relative to this pixel, and you would say that this pixel is hypoechoic relative to this pixel. How about in this instance? Which one is hypoechoic and which one is hyperechoic? Well, this would be hyperechoic because it's a brighter shade than this pixel. This pixel would be hypoechoic relative to this pixel because it's a darker shade of gray. And how about this one? We can see that they're actually the same shade. And the terminology used to describe this, I haven't told you about yet, and that is isoechoic. These two pixels are isoechoic relative to one another. So we talked about how the machine can generate a pixel, and we're going to put all those pixels together to create the image. How does the ultrasound machine assign a location for that pixel? Well, it just does, right? Well, that's wrong. I know that's what you want to say, but you're wrong. Well, the machine is calibrated to interpret sound that is traveling through soft tissue. So to be able to do that, you have to know approximately the speed of sound in soft tissues. I'm going to tell you now, it's 1,540 meters per second. That number really has no use to you whatsoever, but for some reason, ultrasound people really enjoy that number, 1,540 meters per second. So now you know the number, and at your next family gathering or party, you can wow all your friends and family with the speed of sound in soft tissue. Knowing the speed of sound in that soft tissue and knowing the time between when the sound was generated and when the sound returned, you can then calculate the distance from the ultrasound machine that your target is. So let's take a look here. We can see our ultrasound machine generating the pulse. It goes out and hits multiple targets, and then you get return of signals. Those signals return at different times. And because, again, we know the speed of sound in soft tissue, and we know the time that it took for the sound to return, we can then apply our appropriate pixel to the appropriate location on the screen. You can see the red signal here is a bright reflector, and it's also closer to the probe. Well, the time that it took for the signal to return there was the shortest, and we know that it returned to this location of the probe. So if you look at our screen here, it's closest to the top of the screen, whereas this reflector here was a weaker reflector, and it took a little longer for that signal to get to the probe. It returned to the probe at approximately this location. It's going to apply the pixel at this area of the screen, which is a little bit deeper from the surface. And then this reflector here really didn't return any sound at all, and we did not receive a return of signal in this area, so it just applies a black pixel. So let's watch that one more time. The recurring theme for this presentation over and over again is going to be oversimplification, and that's certainly what I've done so far. The reality is that within your targets or in the far field downstream from your ultrasound probe, there is numerous targets. Therefore, there is going to be numerous return of echoes. As that pulse is generated, it's going to hit all kinds of different interfaces, and you're going to have numerous signals returning that look something like this. The machine will send one pulse, and then it's going to listen for all the different echoes that are returning. The fact is that the ultrasound probe actually spends most of its time just listening, not actually generating sound. If we were to take this a step further, and again, I've oversimplified this, this animation implies that the machine is sending one pulse of sound for each depth that you're actually interrogating. That's not true. This is just to oversimplify to illustrate a point. It sends a sound and then it listens for that signal. Well, within that returning signal, there's varying amplitude of that returning signal. Again, that amplitude for that very specific echo that returns from that specific location is assigned a specific pixel. This is called B-mode ultrasound. This is going to be the most common mode of ultrasound that you're using. And the B in B mode stands for brightness mode. It's also called grayscale, and that's very intuitive because you have a whole host of shades of gray that is applied to the screen. Another common mode that you're going to use with ultrasound is called M mode, and the M in M mode stands for motion. Well, up here you have your B mode ultrasound that you are now familiar with, and this down here is your M mode ultrasound that I'm going to explain to you. When you activate M mode, you're going to see a line drop across your screen. You're going to position that line on your B mode image. And then the ultrasound is going to spit out an image that looks like this. And what you have here is the motion of the tissues at the location of this line over time. So on your x-axis, this is time. On your y-axis, this is the motion of those tissues. So what we have here is the heart, and this is a parasternal long axis view of the heart. It's okay if you don't know that. We'll explain that later. And up here at the top is the right side of the heart. This is roughly the right ventricular outflow tract. And you can see this subtle anechoic stripe or black stripe here. This corresponds with the right ventricular outflow tract. This would be the interventricular septum. And then this right here would be the left ventricular chamber. This here would be the posterior lateral wall of the left ventricle. And this bright white line, or hyperechoic line, is your pericardium. And that's seen right here. And you can see over time that tissue is moving. And this is actually during systole. When the muscle of the left ventricle contracts down, you can see that your chamber actually gets narrower, and then it relaxes. And there is a change in pressure gradient, and blood flows from the left atrium into the left ventricle, and we can see our chamber actually dilates here. Probably the most common application for M mode is going to be measuring the heart rate of a fetus, be it an intrauterine pregnancy or an ectopic pregnancy. Now you can see here, this is in an ectopic pregnancy. You can see the heart beating here. The M mode ice pick has been placed through the heart, and then we'll activate that, and you can see the M mode printout. If you look closely right here, you'll see these wavy lines that correlate with the beating heart. Now, all of this looks like wavy lines. You can tell that this is the actual beating heart in this area because you can see right here we have a scale that correlates with the scale on the side of the M mode image. So the heart was beating roughly in this area. We can follow that over to our scale. That's 2 dots up from the bottom right here. So we can say somewhere in here was the beating heart. And I'll be honest, this M mode image does not project very well. I think that when you see this in real life, you'll see that it's much easier than what it appears here. Okay, the next thing I want to talk to you about is gain. Gain isn't really a mode of ultrasound, rather a feature of ultrasound. Now remember we talked about as the ultrasound waves travel down through the soft tissues and return to the probe, those sound waves are attenuated. And that means that the signal is getting weaker and weaker. And in some instances, the signal is so weak that the ultrasound can't detect that returning signal. What you can do is turn the gain up on the ultrasound machine. So basically, you're asking the ultrasound probe to listen harder for returning echoes. Now, you might be able to imagine when you ask the ultrasound probe to listen more carefully for returning echoes, that's going to make the entire screen more white, more hyper-echoic, because you're increasing the sensitivity for those returning echoes. So what we have here is a ultrasound clip of the eye, and you'll notice right off the bat, it's quite hyperechoic in the periphery, but in the actual vitreous chamber of the eye, it's anechoic. But as we turn that gain up, you'll notice the entire screen becomes more white, and then you can actually see echoes within the vitreous chamber. And what that is actually a vitreous hemorrhage. So it's going to get brighter white, and now you see those echoes in the vitreous chamber. Additionally, you'll notice in the posterior aspect of the eye, there's also a retinal detachment, but that's another lecture for another day. This concludes part 1 of the ultrasound physics and fundamentals discussion. In the next installment, we're going to discuss ultrasound probes, probe orientation, and probe movements. As always, please let me know if you have any questions. I can be reached at the email on your screen.